Welcome everyone to the next Gen 4 International Forum webinar presentation. Today's presentation on evaluating changing paradigm across the nuclear industry by Dr. Jessica Levering will be presented. Before we get started, there's some housekeeping information that we like to go through. Doing today's introduction is Dr. Patricia Pavier. Dr. Pavier is the group leader of the Radiological Materials Group at Pacific Northwest National Laboratory. She's also the chair of the Gen 4 International Forum Education and Training Working Group. Patricia.
Thank you so much, Berta. Good morning or good evening, everyone. It's a real pleasure to have Dr. Jessica Levering with us today. She's the American Nuclear Society winner of the November 2020 Pitch European PhD research. I'm very happy that she's with us contributing to this webinar. It's important to have the younger generation presenting as well as the other more senior scientists. So she's the co-founder of the Good Energy Collective, a new organization working on progressive nuclear policy. She recently completed her PhD in engineering and public policy at Carnegie Mellon University. Her dissertation focused on how commercial nuclear trade affects international security standards and how very small nuclear reactors could be deployed at the community level. She's a fellow with the Energy for Growth Hub, looking at how advanced nuclear can be deployed in sub-Saharan Africa. She was formerly the director of the energy program at the Breakthrough Institute, a pioneering research institute changing how people think about energy and the environment. So thank you so much, Jessica, again, for volunteering to give this webinar, and I am giving you the floor. Thank you.
Thank you, Patricia, for that introduction, and thank you to the Generation 4 International Forum for having me. Let's see if I have control. There we go. So the talk I'm going to give today is a little bit of a condensed version of my dissertation. I tried to keep just the most interesting parts, but I'm looking forward to plenty of time for questions at the end. So to get started, this may be obvious to people, but I think it's important to say again that the world needs a lot more low carbon energy. So the Intergovernmental Panel on Climate Change argues that the global energy system needs to reach net zero emissions by 2050 to avoid the worst impacts of climate change. And for that reason, the International Energy Agency has concluded that global nuclear capacity would need to double by 2050 to keep the world under 2 degrees of warming. The power sector should be the lowest hanging fruit for complete decarbonization due to the diversity of low carbon options that we have, but even here the world is not on track, and that's what I'm showing in this graph on the right. So this is showing the global share of electricity coming from low carbon sources, and you can see that it's been kind of flat around 36% since the 1980s. There's been a lot of stagnation and even decline of nuclear generation in the West, and that's part of what's led to this stagnation in low carbon energy globally, but there is a very large potential for growth in emerging economies, and that's what I'm going to focus on for a lot of this presentation. Okay. So this potential for new nuclear and emerging economies is really highlighted by this map, which is from a study that was done by the think tank Third Way and Energy for Growth Hub. And what they did is they projected the global electricity demand would double by 2050, with over 90% of that growth coming from outside current high-income countries. And what's interesting is actually most of that growth is in countries that are interested in nuclear and will likely be ready to host their first nuclear power plant by 2030. So on this map, and this is an interactive You can find it on the Third Way website if you want to play around with it. The size of each circle represents the magnitude of the projected increase in energy demand for each country, and the color is the readiness for nuclear. So you can see how those two projections overlap. And what's important here is that almost every country that starts a commercial nuclear power program first imports the technology from one of the big vendor countries. And this will likely be the case for most of these newcomers as well. And what's interesting for our work is that most of these countries that are pursuing commercial nuclear power already have agreements in place with Russia and China, so-called nuclear cooperation agreements or memorandum of understanding, and they vary on how concrete they are, how much they're about safety and security, or whether they're about actual trade in commercial nuclear reactors. But not a lot of these countries have agreements with the US. And I know we've got an international crowd today, but I'm going to be a little bit focused in this first part on the US's role in the global nuclear market and what that looks like going forward. And this map is from a great report from the Global Nexus Initiative that I encourage you to check out if you haven't seen it already. So this trend of the US being somewhat absent from the global nuclear market has been going on for a long time. So this chart that I'm showing is the total amount of nuclear exports by decade and by country. This is commercial nuclear reactors by gigawatt. And so you can see this light blue color is US exports, and the US was the dominant exporter for the 60s and 70s, but then declined to very little. Whereas Russia, it was the Soviet Union here, but Russia now has sort of maintained a good share. We're just starting to see South Korea. France has sort of maintained their share, and China's actually on here with their one project in Pakistan, but it's too small to show up, but they have big ambitions. So China and South Korea have big ambitions for exports going forward. So you can see a similar trend in all sorts of data: nuclear R&D by country, nuclear patenting, fuel exports, research reactors. And why this is interesting to us is that it has a lot of implications about this geographic shift in power and what that means for international security, safety, non-proliferation regimes. And so for the first chapter of my dissertation, this is what I looked at as the implication of this trend and what sorts of policies could be implemented to strengthen US influence going forward. So this work has been published. It was published last year in the journal Energy Policy. So if you're interested in this side, I encourage you to read that paper. But the main questions that I was asking in this research was, what was the role of commercial nuclear exports in setting international safety, security, and non-proliferation standards historically? What strategies might strengthen US influence in global nuclear security regimes? And how effective and feasible are these strategies? And I'm going to go through this work pretty quick because I think you'll probably be more interested in the microreactor stuff, and this work's already been published. So just big picture, we developed a series of strategies. You can think about these as sort of policy packages for strengthening US influence in international regimes. And to evaluate them, we brought together this participatory workshop of experts in September 2018. It was a 2-day workshop with experts from a mix of nuclear energy and security fields. We also pulled them from think tanks, academia, government. There were pre-readings and introductory presentations to frame the conversation, and then our experts evaluated our foundational premises, kind of our assumptions around these historical trends, and then these 6 proposed strategies that we put forward. They also brainstormed 4 additional strategies that were evaluated along the same format. And I'm just going to jump to the big results from the workshop. So going into this workshop, a lot of the literature on, especially coming out of U.S. security space and U.S. Nuclear energy thought leadership was really focused on export control as the big obstacle for the U.S. We could be more engaged, we could be doing more commercial exports, but our export control is just too constraining. From our group of experts, export control was really not seen as the main obstacle. They thought we just didn't really have a product worthy of export, or that we couldn't do big nuclear export projects. So the focus was really on how do we sort of reinvigorate and strengthen the commercial nuclear sector so that it's competitive with the other big vendor globally. So unfortunately, expensive and radical policy programs to commercialize new reactors were not really seen as feasible. Maybe that's not surprising. We did put forward a few diplomatically focused strategies, and these were viewed as much more effective at strengthening U.S. influence, but especially difficult at the time. This was during the Trump administration, so not very feasible to implement, although they did think they could be implemented with a different administration. But the big takeaway overall was that the experts just didn't think the U.S. could compete with large light water reactors. And that last phrasing is key because there are a lot of non-light water reactors under development in the US. And they agreed that, advanced nuclear technologies could be cheaper, faster, safer. The US could have an advantage if they could get them commercialized. So this map is from a report from the think tank Third Way, maps out advanced nuclear projects under development. It's now worldwide if you want to look at it. But the US has over 60 advanced nuclear companies working on commercializing new technologies. And so the question that we discussed with the experts is, are any of these going to be ready fast enough in time to be competitive on the global market? And the experts were a little skeptical on that front for those that were familiar with what was going on with commercial nuclear. So they really, there was a lot of skepticism about how fast these commercials could be, how fast these technologies could be commercialized. And the 2 concerns were really founded in existing literature and evidence. So the first is from this Secretary of Energy Advisory Board from 2016, and they found that commercializing a single advanced reactor design in the US could take decades and cost about $25 billion. So they didn't see that the US would be willing to commit that type of money to commercialize a single reactor design. And then there's a complementary paper from Abdullah et al. 2017 that found that the US government has not been investing nearly enough to commercialize advanced reactor technologies. So at the time, I wanted to look into a little bit more, how fast new nuclear technologies could come to market, if that's changing. And there were really 2 big trends that stuck out that our experts really didn't know about. They didn't know the status of what's going on with advanced nuclear in the US, which is moving very fast. So 2 things that we kind of highlighted after the meeting is there are several advanced reactor vendors moving towards licensing in the US and Canada, especially small and very small modular reactors. Since this workshop, there's already been some licenses submitted. And there's a big move towards private funding and financing and seeking niche markets to build a commercial demonstration without government involvement and on much shorter timescales. So I wanted to explore how this might change the export market and the US's chances of being competitive. And in particular, I'm going to focus on very small modular reactors because they seem to be able to maybe move a lot faster than even SMRs. So for the rest of the presentation, I'm going to be referring to these as microreactors. I know in Canada and other places they call them VSMRs, but what we're talking about is anything smaller than 10 megawatts electric. There's a lot of other properties that go in there, but what we found is that microreactors, could be a marketable export product, and they might also come with some security and non-proliferation benefits. So it's worth exploring. Most of the main nuclear vendors, the big countries, are focused on large light water reactors, although of course there are some great SMR programs around the world. In the US, we do have several companies. It's growing up to maybe more than a dozen now. Private US companies working on microreactors, and they're aiming to commercialize and demonstrate even faster and earlier than SMRs, and definitely before large advanced nuclear technologies. And they could have some international security benefits. So a big one that I like to focus on is lifetime cores. So this means that there's no on-site refueling, and this could help facilitate a build, own, operate, remove export model, which could be very attractive for certain countries. It could also get commercial nuclear into countries much sooner than large light water reactors. And importantly, this Boer model avoids many of the security challenges of nuclear newcomer countries. So you don't need to develop domestic fuel handling and waste storage facilities. So that could be very beneficial. So I said that microreactor developers were targeting niche markets. So they're looking for places that pay a lot for energy already. And so even the first of a kind cost of a demonstration might be cost competitive with existing energy prices. So there's only a few places where this might work, but one of them is in diesel dependent off-grid communities. So islands, but also certain countries like Canada have a large number of off-grid communities that are dependent on diesel. This is a map of them. The blue lines here are the existing power grid, and the circles are all the off-grid communities. And the population actually adds up to quite a bit, but their individual electricity demand in these communities is quite small. It's even too small for an SMR in most cases. So what I wanted to look at with this second chapter in my dissertation is, could microreactors actually make sense for such communities? And so the questions that I was looking to answer with this work were, under what conditions would a small nuclear reactor be the optimal choice for a microgrid installation, specifically an off-grid application? What would the microreactor need to cost to be cost competitive with alternatives for microgrids? That's mainly diesel, but also renewables and batteries. How important is load following for microreactors? Because again, they might be operating alone on a microgrid or with renewables. And how sensitive is this optimal choice to diesel fuel prices and then parameters of the microreactor? So just at first glance, very simple estimates. It looks like microreactors could be cost competitive with diesel, and that's why these companies are looking at diesel dependent communities. This bar chart here is just showing a really rough estimate of levelized cost of electricity for a microreactor and for the range of diesel generation globally. So you can see that for diesel, almost all of the cost is in the fuel, and this bar here represents the range of diesel prices globally. So It's a very big range. And for the microreactor, for this chart, I just essentially doubled all the costs of a light water reactor. That's based on public numbers that I've seen, just rough estimates, to give us a first order approximation. And it looks like it could be competitive, but we really want to know what capital cost, what load factor, what diesel price. Is this true at the local level? So that's what I did, a much more detailed study for this research. So what I wanted to do was actually model some real communities that might use microreactors. And to do that, I used this software called Homer that's developed by the National Renewable Energy Laboratory here in the US. And what Homer does is it finds the least cost grid mix to meet a specified electrical and thermal load, if you have it, based on the generation options included. So it does hourly load. So you have to have a year's worth of hourly load for the community you're looking at. And then it makes sure that your mix of technologies can meet that load, and then it optimizes over cost. What's nice about Homer is it includes a very big catalog of generic technologies, renewables, fossil, battery, with cost and performance, as well as links to weather data and renewable resource data by location. So you can get very granular data for this community, and you need that weather data for things like battery and thermal performance for your generators. So I was able to get real data for a set of case studies. I had 2 communities in far northern Canada that are currently off-grid diesel-dependent communities. I'm calling them Community A and Community B, but they are in northern Quebec, and their loads are just a few megawatts on average. I also did a large hospital complex in Fairbanks, Alaska, and then I had the University of Wisconsin Madison campus. I wanted to do a college campus just to see what it looks like. These latter 2 cases are grid connected, so it's harder to make the case for a microreactor, but I just wanted to see how the performance looked for a microreactor. For the rest of the presentation, I'm going to focus just on Community A to show you what the results look like, and you can see the other results in the paper that's coming out soon. So for each of these case studies, what I did is I modeled 4 microgrid systems, constraining the deployable technological mix in each to compare their cost and performance. And so what Homer does is it optimizes with whatever technologies you allow it to have in each case. So the first mix was the business as usual. It was 100% diesel. I did it over a range of fuel costs to test out the sensitivity. The first mix 1 was 100% micronuclear. So Homer actually doesn't include nuclear. This is maybe not surprising. It is a renewables focused microgrid program, and most people don't think about nuclear when they think about microgrids, but it does allow for you to make your own generators. So I developed a generic 1 megawatt microreactor component with nuclear specific parameters, heat rate, fuel density, things like that, fuel cost, taken from some NEI reports and IEA reports. And so after the 100% micronuclear case, I looked at nuclear with diesel, so allowing Homer to optimize over microreactors and diesel generation. And the last mix was nuclear and batteries, because there's some people arguing that batteries could be a good complement to nuclear for load following. And then all 4 of these cases, I first did without and then with renewables included. It's just easier to do the optimization separately to see what changes. And I will show those results. I will point out that this community is very far north and it's very cold in the winter. So renewables didn't make a lot of sense, but that's not going to be true everywhere, of course. So just that with that caveat. So the big results here were that the optimal system really depends on your constraints, but nuclear with batteries was the cheapest option and the cheapest low carbon system. So depending on what you care about, if you just care about lowest cost or if you care about low emissions and whether or not you want to include nuclear or exclude nuclear from the system, it changes what your optimal system is. But you can see here that because nuclear, the micronuclear was cheaper, specifically cheaper than diesel, it's both the lowest cost and the lowest emissions system. So the optimal system here was actually 3 megawatts nuclear, so 3 microreactors, and then a very large battery it gives an LCOE of 16 cents per kilowatt hour. Now, if you exclude nuclear, the cheapest option is going to be diesel with a good amount of wind, but of course that wind comes and goes. So that's why you still need that 4.1 megawatts of diesel. Now, if you really want to exclude nuclear and have a low emission system, that gets really tricky in a community like this. You have to very much overbuild the renewable system. So the optimal system for 100% renewables includes 54 megawatts of PV, 21 megawatts of wind, and a 325 megawatt hour battery, which is huge. That's larger than the largest battery installation currently operating, although that might be eclipsed soon. And the levelized cost, as you can see, was over 4 times greater. So for communities such as this, which is very far north in a very cold place, nuclear and batteries makes a lot of sense for them. And it's definitely cost competitive with diesel. So of course, we don't really know how much a microreactor is going to cost. So I did a very large range of potential costs that I justified based on a lot of literature and projections, but it's really going to depend on what these costs end up being. So I did a sensitivity analysis on all the parameters related to the microreactor and the diesel generation. And this chart is trying to summarize a lot of them at once. So bear with me. This chart is showing the levelized cost of electricity from the microreactor as a function of the operating reactor lifetime, so how long that core lasts before you need to replace it, and the capital cost of the microreactor, ranging from $5,000 per kilowatt to $25,000 per kilowatt. In this gray bar is the range of diesel LCOE if your fuel goes from $1 to $2 US dollars per liter. That's kind of a rough range that we see in this region. Some of these communities are even above $2 a liter. Some communities that are closer to the grid or closer to the road network are maybe a little lower than $1, but this is kind of the range where you need to be for the micronuclear to be competitive. And you can see that the microreactor is cheaper than diesel for operating lifetimes sort of above 10 to 15 years, and for capital costs sort of below 15,000, below 20,000. So that's sort of roughly the parameters that need to be met. So the big takeaway is that microreactors can be cost competitive with diesel if, that's a big if, capital costs are moderate and diesel prices are high. So microreactors are currently not competitive with grid electricity. That comes from those other 2 case studies I did. They need a carbon price of about $60 to $120 per ton. And the largest uncertainty really comes from capital cost and also the lifetime refueling model. So what the business plan is for the core lifetime. And this chart just shows, this is a sensitivity chart showing how much the LCOE changes when you change each of these factors by 50%. So the capital cost, the lifetime, operations and maintenance, has an effect, but it's smaller, and then fuel has a very small effect on the LCOE. Okay, so how much are these things going to cost is the big question. And there's a lot of concern in the literature on microreactors, which there's only a very small literature on microreactors, I will caveat, but there's a feeling that they have to be very expensive because they're so small. And this assumption really comes from assumptions about economies of scale. But proponents argue that factory fabrication and economies of volume will outweigh this. So for the last chapter of my dissertation, what I wanted to look at is trade-offs between economies of scale and economies of volume for very small modular reactors. So the big questions that I'm answering in this chunk of research are, do nuclear reactors experience economies of scale, and how large is this effect? What learning rates are expected for factory fabricated SMRs? Can economies of volume from factory fabrication offset potential diseconomies of scale? And where is the break-even point where it makes more sense to do factory fabrication? And where do they break even on costs? And then what sort of the big question from the previous work is, what is the potential range of capital costs for nth-of-a-kind microreactors? And parts of this work have been published in the Bridge, a National Academy of Engineering journal, if you want to go into a little more depth on that. So as I said, there's really no consensus on cost of future SMRs from experts. This chart is from an expert elicitation of nth-of-a-kind nuclear costs from Abdullah 2013, and what they did is they asked experts, how much different size reactors would cost nth of a kind, and they're kind of all over the place. This is a large, 1 gigawatt light water reactor, but they also looked at a smaller 45 megawatt SMR, and you can see it's all over the place, but that is still much larger than a 1 megawatt microreactor. So some of the costs that we've seen recently, there's NuScale. There's a lot of different estimates for NuScale that have come out as they change their reactor size and they change their projections. But at the time this was published, I was seeing 4,400 per kilowatt, and Oklo, which is a 1.5 megawatt microreactor, in their license application, they give an estimate of 6,700 per kilowatt, so that's pretty cheap for a microreactor. But you also see in some of these studies that are microreactor specific, much higher costs. So this paper, Moore 2016, which looks at microreactors in Canada, uses $35,000 US dollars per kilowatt. And Ruiz et al. Uses $130,000 per kilowatt. Now this is very high, and where they get those numbers is by using scaling relations. So we're gonna explore a little bit more about these scaling relations, and I just to warn you, this is going to be my only big slide full of math, so bear with me. But there are two main equations that govern the economics of nuclear costs in theory. And those are scaling relations and learning curves. So this equation on the left is a very standard scaling relation. This is used in all kinds of engineering, all different types of technologies. And what it says is the cost of the smaller unit can be scaled based on the cost of the larger unit, based on the size difference, and then to the power of this scaling factor. So obviously everything comes down to what the scaling factor is for your given technology. And this equation on the right is maybe more familiar to a lot of you. That's a traditional learning curve equation. And again, we see this learning curve applied in all sorts of technologies. It was originally developed for airplane manufacturing, but we see it for solar panels and wind turbines and jet engines and all sorts of things. So what this says is as you build more units of a technology, the cost comes down. And the more intuitive way to think about it is the learning rate. And what the learning rate is when you double production of a technology, how much does the cost decline, by what percent? And there are estimates for both of these, for both the scaling factor and the learning rate for nuclear. In the literature, there's dozens, if not hundreds of studies on each of these, but from the literature, on nuclear, we see a scaling rate of about 0.25 to 1. 1 means there's no scaling effects. From the literature on learning curves, we see learning rates ranging from negative, meaning the technology gets more expensive the more you build, to positive 6%. So that's a big difference. And it really changes how we think about factory fabrication of nuclear. Now, the big problem with this literature is that it's almost entirely based on the US cost history from the 1970s. Even though there's at least 30 studies that look at scaling relations, they're just different kind of formulations, different estimates of the US cost experience. So it's a very narrow range of technologies of history that we have evidence from. So we don't have a lot to work with here in terms of what we might project for future technologies, but I did want to look at this assuming these are true. So to start, let's assume that scaling relations apply. If we do that, microreactors are going to be too expensive if these traditional scaling relations hold. So what I'm showing here is the first of a kind cost for a microreactor based on the capacity, the size of the unit, and then using the scaling relation with different scaling factors from the range that's in the literature. And this is based on the large light water reactor that I'm using in the scaling relation is a kind of rough approximation of an AP1000, so 1100 megawatts. And you can see that for down here for microreactors, the first of a kind cost gets really high, up towards over $100,000 per kilowatt. That's where those numbers came from in those studies I cited earlier. And even for a traditionally sized SMR of 300 megawatts, still double the cost of a large light water reactor, and also still too expensive to be competitive with grid electricity, of course. But there's an interesting phenomenon that maybe makes intuitive sense, but we're starting to see it referenced more in the technological literature. So there's this idea that learning rate may also be dependent on size, more so than intrinsic to a technology. So I think this makes sense. If you're building smaller things on a factory setting, you learn faster the smaller they are. So these are two recent studies. This one is Swartz 2020 and Wilson 2020. And what they did is they collected learning rates from a bunch of different energy technologies across the whole energy sector, demand, storage, supply, and they compared the learning rate versus unit size. And what they found is that learning rate goes up the smaller the capacity of the technology. And both studies find this. They used different technologies, different studies, but they find the same relationship. So what I looked at is how this might apply to nuclear, specifically SMRs. So how might a learning rate that's based on size change how we think about these break-even costs. And also unit size, so how big the reactor is can make a difference in cost declines, because you can just build more units for a similar investment. So what this chart is showing is if how many units of an SMR you need to build to reach cost parity with an AP1000 reactor. So not really any learning, very small learning for the AP1000, but the same learning for the different size reactors. And you can see that this is how many megawatts you need to build. So obviously, if you're going to build 100 megawatts of a 1.5 megawatt microreactor, it's a lot more units of the technology, but that means the cost declines much faster. So the smaller your reactor, the fewer megawatts you need to build to reach cost parity with your large reactor. Again, this is assuming economies of scale applies. But looking at different cost trajectories and different factors that influence them, cost trajectory really depends a lot more on learning rate than first of a kind cost. So this chart on the left is showing kind of a generic SMR with learning curves based on different learning rates from 1% to 25%, sort of the range we see in the literature. And you can see that as you build more units, the cost comes down much faster for higher learning rates. That's obvious. But it's a much more noticeable change than if you change the first of a kind cost for the microreactor, for the SMR. So what we found overall is that learning rate is much more important than first of a kind cost, whereas a lot of the focus in sort of the cost estimates for microreactors for SMRs is really on that first of a kind cost, and people think, oh, that first of a kind cost is too high, they won't be competitive. But there's a lot more that goes into that. So putting this all together, kind of the $1 million question for microreactors is, how many units do you need to build to be cost competitive, and really to be cost competitive with grid electricity. I kind of chose this arbitrary target of $2,000 per kilowatt. I think that's a good cost target for new nuclear. And what I calculated here was how many units you need to build to reach that target, depending on the learning rate and the first of a kind cost. And you can see that if you start, pretty moderate at $5,000 per kilowatt, and you have a high learning rate, you need to build, 10, 100 units before you get down to $2,000 per kilowatt. But if you start high and have a low learning rate, you need to build tens of thousands of units to reach that $2,000 per kilowatt cost target, and that could be much more difficult. But this is sort of a big caveat here, or point I want to highlight is that this is units, not megawatts. So if you're building a 1 megawatt reactor, that's a lot less investment, a lot less cost to bring the cost down the learning curve. Whereas if you're building a very large reactor, even an SMR, it can cost a lot more money to drive down this learning curve, because it's really dependent on learning rate, which is just units built. So that's sort of the big takeaway, is that the smaller you build, the faster you can come down that learning curve. So to synthesize all of this work, and bring it back to where we started in the beginning, the experts who participated in our workshop agreed that U.S. commercial nuclear exports helped strengthen international nuclear security regimes historically, but they didn't see the US being competitive with Russia and China going forward, particularly because of our lack of a vibrant export market technology commercialization. Microreactors could offer security benefits and an attractive export product comparable with or compatible with a Bohr model for nuclear newcomer countries if they can be made cost competitive. It looks like microreactors could be cost competitive with diesel for off-grid applications, but to really scale up and be cost competitive with grid electricity, costs will need to decline significantly. It looks like such cost declines are possible if economies of scale don't really apply to novel designs and if learning rates are above around 20%. So, my PhD was partially in public policy. So I did want to end, this is my last slide, on some of the policy implications or recommendations to facilitate this. So there's this really good paper by Breitz in 2018 that argues that both components of experience curves, so the cost and the deployed capacity, are affected by policy and politics. They're not just something that's intrinsic to the technology. So therefore, if we want to bring down the cost of nuclear, we need policies that facilitate deployment across the commercialization timeline. So we need demand-side policies that foster these first few dozen builds and have that concrete order book in place. We need modernization of licensing that is appropriate for mass-produced reactors. And we'll need new export regimes for build, own, operate, remove models with SMRs and microreactors. And of course, the levelized cost is also really dependent on the cost of capital. So another thing that's important is support for financing to bring down the cost of capital, to reduce the discount rate in that LCOE calculation. And there's lots of other things, and we can talk about them in the Q&A, but that's my last slide, so I'm going to kick it back to Berta.
Thank you, Jessica. If you have questions, and I know there are several in the Q&A pane already, type those in now, and while those are coming in, we'll just take a quick look at the upcoming webinar presentations. In August, a presentation on graded approach, not just why and when, but how. In September, experimental R&D in Russia to justify sodium fast reactors. And in October, metal fuel for prototype generation 4 SFR, design, fabrication, and qualification. Give me just 1 second, Jessica, I'm gonna get you. Okay, so in the questions pane, you now have access and should be able to see those come in. The first question, does Russia policy of leasing or taking back their spent nuclear fuel play a role?
Yes, there's a lot of extra services that Russia offers that make exports from them very attractive and cooperation agreements with them very attractive. And China has been looking at doing something similar, and so has South Korea, in terms of helping with financing, helping with supply chain. Fuel takeback is a big component, and that's something where we see, the U.S. is really at a disadvantage because not only do we not do fuel takeback, but we also don't have a domestic or a very small domestic fuel supply and no domestic policy on nuclear waste. So that is one area where different models of SMRs and microreactors going forward from the US could make them more attractive export products. If you can do this this build, own, operate, remove model where you take the microreactor back, the whole thing back. Countries really like that idea, especially much smaller countries that don't want to develop their own fuel handling and fuel processing facilities.
Great, thank you. The next question deals with private level funding due to competence in the private sector, but not in the government laboratories.
No, you know, I think there's wonderful capacity in the national laboratories. They're just they're not as set up to do commercialization, and that makes sense. They're doing early stage research, and they are doing, you know, helping remove the risks of a lot of these technologies, the, you know, development risk and financial risk of a lot of these technologies, and figuring out what they need to be commercialized. But in terms of turning a technology into a commercial product, that's something that private financing and private investors are better at seeing, at understanding the market needs, you know, developing business models that meet those market needs, you know, understanding what utilities want, what customers want from nuclear technologies is much more, makes more sense in the private sector. And in the US, of course, you know, it's different than most other countries. We have a very robust startup ecosystem with a lot of venture capital and private financing. So there's also just a lot of excitement around climate tech and clean energy. And so there's a lot of money that's going into all sorts of solutions on the clean energy side. And so there is a growing set of investors that are very interested in nuclear technologies. And you see this at kind of every level, you know, traditional venture capital, but also angel investors and kind of newcomers to the climate tech space. So it's not in place of government investment. It's just different parts of the commercialization timeline.
Great answer, thank you. How is the capital cost of microreactors calculated to compare with the diesel generators?
So for the modeling that I did with the microgrid systems, I used a big range of estimates for nuclear fuel costs, nuclear O&M costs taken from existing industry, but I made it much larger because, you know, we don't quite know. And then I used a big range of capital costs for the microreactors in those. So I did just a lot of sensitivity analysis, but the kind of baseline cost that I used for a lot of those, like the middle of the road for those case studies, was $10,000 per kilowatt for the microreactors. I think that's what the question is asking. And then I did the same for diesel. I used a big range, but I also, for the baseline, I used the cost of diesel in those communities, so the real cost of diesel.
Great, thanks. I don't know if it will help. We can go back to slide 18. This question actually references slide 18. What nuclear modeled, I don't know what
that means.
Yeah, I was struggling with trying to figure out if there's a typo in that word or if I'm just, that's a word I'm unfamiliar with.
Endogenously in the mixed models. I don't know. I used, so I developed this one generic 1 megawatt microreactor, and what Homer does is it picks the optimal number of those microreactors to build in the system to make the lowest cost grid that meets the hourly load over the whole year. Okay, maybe they can ask again.
Yeah, some clarification there. For a reactor factory to be built, do we need DoD to order 1,500 reactors to justify building the reactor factory?
No, not necessarily. For any of these, the first few are going to be bespoke. They're going to be, you know, custom built or hand built. you probably only need, maybe more than 10. For some of these companies, especially the smaller side, that's really their focus right now, is building out their order book. So Oklo, the 1.5 megawatt reactor plan, is looking at customers beyond their first few demonstrations. You do need an order book of some length to justify those investments in the full factory. But part of that early learning curve is your first few, maybe your first several, are going to be more custom built, and that does allow you to do a lot more learning in the early stage before you commit to a factory and a really standardized design. And it's probably not going to be DoD also, because it looks like we're going to keep the defense and civilian microreactors separate for the most part. There might be some companies that do both, but yeah, you definitely do need an order book, and we know this from looking at learning curves for large commercial aircraft. But how long that needs to be, it can be just a dozen or so units.
Great, thanks. John Kelly has a question. Is there a theory on the economy of mass production that is different than the economy of scale?
Yes, it's called economies of volume. And that is the learning curve. That is when you build something in a factory, costs come down with more you build. And what we're seeing, we see learning curves for all sorts of different energy technologies. We don't really see them for large nuclear, but that makes sense because we haven't actually built nuclear in a factory setting. So why would we see learning curves? With regards to the scaling relations, the scaling factors that were calculated were over a very narrow range of sizes, so sort of above 500 megawatts. It's really unclear if that same scaling relation applies when you get to very radically different designs like a microreactor. The scaling relations are really meant to apply to the same technology that's just a different size. So you take an AP1000 and you scale it down to 1 megawatt. That's obviously not what's being done with microreactors, but that's what's baked into those scaling relation assumptions. So I, personally don't think that scaling relations apply over the full range of sizes for nuclear reactors, from 1 megawatt to 1.6 gigawatts. But you definitely could see some diseconomies of scale with SMRs, but how big of an effect that will be is up for debate, especially if the engineering is much simpler.
Great, thanks. There's a question, I'm going to reword it just a little bit. My apologies to the person who asked it. Are you optimistic about the investment given a 6% learning rate?
I don't think investors are really, we don't know what the learning rate would be. With a 6% learning rate, even there you see significant cost declines for smaller reactors, because it's just costs much less to build more of them. So you still see costs come down pretty fast. And if you're starting at not so high of a first of a kind cost, like Oklo saying, 6,700, even with a 6% learning rate, they come down pretty fast. But also the reason they're looking at niche markets is because they're already cost competitive with their first of a kind cost. So for an investor, if you're going to be making money on your very first demonstration reactor, that's a lot different than having to wait to build 100 units before your break even. So for example, with large wide-body aircraft, Boeing and Airbus, they needed to build a few hundred aircraft before they actually break even on cost. They're selling them at a loss. It's possible that Airbus, for their latest wide-body aircraft, actually never broke even. They never got down to cost, but with microreactors, you can start with niche markets where you're cost competitive from the very first unit, and then as you come down the learning curve, you open up to new markets. So eventually you might reach, states that have higher electricity costs, like California, like Hawaii, and then you might, if you keep building, get down to where you're grid competitive in more places. So even with that 6% learning rate, yes, and there is a lot of investors already investing in microreactors, particularly because just the total cost of a unit is so small. Even if it's very expensive per kilowatt, it's only 1 megawatt, so a few $1 million isn't that much for an investor.
Thank you. Recognizing that standardization is economically critical, how are we going to down select on what small or microreactor technology will be commercialized?
Well, I don't think, well, the big question I have about this question is who is we, who is doing the down selection. I think it's going to be, or it should be, a little more left up to market. So I think you want to have a good commercialization ecosystem to help more technologies get through licensing. But right now we're seeing, several companies start licensing in the US. Two have already submitted, one, NuScale submitted a design review and Oklo submitted a combined operating license. I think we're going to see a lot more of those in the next 5 years. And then we'll just see who, what the cost comes out to be, what the performance looks like for these different demonstrations, and that's how it will be decided. So based on performance and cost, who can build out their order book, who can get more customers lined up, and that's how it's gonna, that's how not we, but customers are going to be selecting which SMRs and which microreactors will be successful. I think for what's being commercialized, we're not really seeing a down selection. We're seeing a lot of different technologies, over 60 advanced reactor companies in the US are kind of all working towards commercialization. So I think it's good to have that diversity because we really don't know what the market wants. And that's been a challenge in the past when you've had commercialization efforts focused at national labs and through governments as they pick one technology, put all their eggs in that basket, and then there isn't a market for it, or it doesn't actually meet the needs of utilities. And so instead, building out more of this, definitely still have strong government support for that, that technological development, but it's more on the infrastructure side. So building out, testing facilities, licensing capabilities to help more companies get through to fully commercially available. But then it's going to be competition for customers.
Great, thank you. Since electric market is so competitive, should nuclear reactor focus more on meeting industry's thermal needs and co-produce electricity?
Yeah, it's definitely something that is being looked at, and I actually, in the latter two case studies that I did, I had thermal demand data, so I looked at combined heat and power. The more revenue streams you have, the easier it is to be commercially viable. So you do see a lot of these reactor developers looking at cogeneration, whether it's heat for industrial applications. There's a lot of vendors looking at that, particularly high temperature gas cooled reactors and molten salt reactors. You're also looking at hydrogen production and desalination to some extent. And the other one that is really important from a utility perspective is grid services. So things like having peaking capabilities, on-site storage, which you're seeing in some of the molten salt designs, being able to offer more complex services to the grid rather than just kilowatt hours is becoming more attractive, especially when we have more variable renewables on the grid and more concern about reliability and resiliency. So there's definitely, again, this is where that having a diversity of design. So different reactors are going to make sense in different markets. Industrial users might want something different than an off-grid community of 2,000 people.
Thank you. Any rough numbers on how much nuclear capacity would need to be installed to replace diesel generator dependent communities in Canada?
I could give you that number. The total market is not huge in, adding up, most of those communities are quite small. I think it's less than a few hundred megawatts. So it's a lot of, 1 megawatt reactors, but the total market size is not that big. Another big off-grid market is Australia. They have it's kind of a I call it like an archipelago of microgrids. They have a lot of off-grid communities as well. And then there's, worldwide, it's much larger, of course, but for this niche market, Canada is really attractive to a lot of these developers because they pay such high costs for electricity right now.
Thank you. Regarding learning rates, do you think a one-size-fits-all model is too simplistic as learning rates vary by technical discipline? Easier for high learning rate to control, say, than vessel manufacturer. Also, learning rates are factory, site, plus country dependent.
Yes, I think.
How relevant is it to the investor?
So I think learning rates depend on a lot of different things. Technology, of course, but also, how innovation is handled and how changes in design are handled, how regulation is handled. Do you have to submit a new license every time you change one little thing? And that's why I highlighted on the last slide that paper that talks about how policy affects learning rates. And that paper was looking at energy technologies, but there's some good case studies on how learning rates for things like wind turbines differ in different countries because of the policies they have in place. So I think there's a lot more that we can learn from different energy technologies, but definitely from an investor perspective, you want to make sure that you are able to take advantage of learning and not sort of locked into a design that you can't change. So there's a trade-off between standardization and ability to innovate. And we've seen this in more recently things like commercial spacecraft. There's definitely benefits of standardization, but you also want to be able to change the design when you learn, because that can be also bring the cost down through innovation, not just through getting better at processes in your factory fabrication.
Great, thank you. For newcomer countries that are looking to deploy large nuclear plants as baseload sources alongside renewables, how we avoid the challenge of the duck curve and the costs associated with overcapacity during the day?
Ooh, okay, that's a complicated question. I think there's a couple challenges there. So one, countries that are looking at large nuclear, there's not as many, but there definitely are a few dozen countries that are looking at importing large nuclear reactors. Nuclear is not a huge share of their electric grid right now. I mean, their first plant wouldn't be a huge share of their electric grid. Depends on the country, of course. And then they also don't have very high renewables penetration in a lot of these places. If you have a specific country in mind, ask the question again. I have spent a lot of time looking at the potential for nuclear in sub-Saharan Africa and Southeast Asia. But right now, for large nuclear, for countries that are looking at building their first large nuclear plant, that is almost entirely going to new demand. So they would be growing their total electricity generation. And for most of these places, they don't have a huge set of renewables in place. It's more fossil fuels that they're complementing, or hydro, which is easier to complement. Duck curve. I think that's a very separate question. That's oversupply of solar at certain times of day and undersupply at other times of day, and eating into the peak demand. There are some good studies looking at load falling with nuclear, even for large reactors on large grids, and there are benefits to load following, even with existing nuclear on large grids. So email me and I can share that with you.
Thank you. The U.S. has been taking back fuel from research and test reactors. Can this be a model for a U.S. take-back program?
Yeah, definitely. I don't know much more to say about that. It's different because research reactors are much different and the fuel's much different, but it's definitely something we can do. And, historically, the U.S. was the dominant exporter of fuel as well. So it's, not impossible for us to get there again. I think something more likely is building out a more diverse fuel supply, more internationalized fuel supply, where you have more diversity in who you can buy fuel from, but also having the US be able to offer fuel take-back services is really important. And so finding easier ways to do that, or incentivize that policy-wise, could be very helpful.
Thank you. How important to these costing models is the relative need for an on-site civil works for microreactors versus SMRs versus LWRs, et cetera?
So that's built into the capital cost assumption. I'm assuming you mean sort of like the infrastructure that needs to be in place, or the construction that needs to be done before the reactor comes. I'm not quite sure what the civil works question is, but a lot of the microreactors are going more with a model of kind of plug and play, so very minimal on-site infrastructure is needed. Before, it depends, some of these are below grade, some of these are above grade, so it's different. Whereas you also see a big diversity again in SMRs, so some are being designed to be deployed in multi-unit packs like NuScale. That has, of course, a lot more infrastructure that needs to be built before the reactors come. But again, it's this diversity question. We're not sure what's going to make the most sense, and it's also going to be different for different communities. A community of a few thousand people, they want something really easy that just gets delivered and you plug in, like a diesel generator. So they're going to want something with much less kind of infrastructure needed to be built ahead of time, whereas a town that's looking to replace its large coal plant might already have a brownfield site where they can do a lot of that preparatory work for a large set of SMRs. So it really depends on the customer.
Great, thank you. What fuel form was assumed? Did you look at what most developers are talking, like the Trizo or the HALEU, HALEAU?
Yeah, so I looked at HALEU for this modeling because I was sort of basing this, although I did a generic 1 megawatt reactor, Some of the parameters are based on Oklo because they've submitted an operating license, so there's more information available from them, but I tried to keep it pretty generic. So I looked at, a range of uranium prices, a big range to kind of capture all the uncertainty there. But fuel, even if you double the cost, quadruple the cost, it's not a big component of the levelized cost for nuclear. But I did, play with a big range of costs for the fuel. It doesn't matter so much what the fuel is in this modeling because it's mostly an economic model, although there is, performance factors in there I recognize, but I did assume a HALEU fuel.
Is there differentiation in the reliability of operation for different generators? If so, how can this be quantified for micronuclear generators?
I'm not sure if they mean different nuclear generators or different fuels comparing nuclear with fossil. There's definitely differences in reliability. There are parameters in the Homer model that you can adjust, and I did play with. So things like required operating reserve, minimum operating power, ramp rates, those sorts of factors I did play with for the microreactor. And nuclear has advantages. There, but right now for if you're doing 100% nuclear, you do have to do load following, of course, but you can do it with oh, sorry, it's still before 7 in the morning for me. What is the word I'm looking for? Steam bypass, sorry. The very simple answer is you can just do steam bypass if you need to do really fast load following, and that's what some of these microreactor developers are looking at doing rather than complicated maneuvering or power cycling for microreactors. So there are definitely benefits in terms of reliability for nuclear, but it's and that's also why Canada has been so interested in SMRs, is because delivery of diesel fuel is actually really challenging in a lot of these places. It gets delivered by truck or by boat, sometimes even by airplane, and that can be really hard, and if there's a storm, and so having a on-site generator that needs to be refueled every 10 years is really attractive. And that's something that's very unique to nuclear and why it's being pursued in these places.
Thank you. So there is some clarification on that previous question regarding the scenario modeling. There could be some endogenous, and I don't know if I'm pronouncing that right, endogenous and exogenous variables. Sometimes the optimization models are forced with exogenous variables to make them more realistic, to avoid the results like you got in the fourth scenario, low cost, zero carbon with no nuclear. My question was related to this. Was some nuclear capacity modeled as endogenous? But please ignore if I still sound confusing.
Yeah, I'm not sure what they mean by that. So the way Homer works is it's not a very complicated model. You say, okay, here's the demand for every hour of the year. You can build diesel, you can build nuclear, you can build batteries, you can build wind and solar. Try every combination of those and tell me what's the lowest cost option that meets demand with a certain margin, like 25% reserve or something. And so Homer, when I say it's not complicated, it really just tries every combination. It tries 4 microreactors and 3, and it tries 10 wind turbines, and it tries 0 wind turbines. And every sort of possible mix. And it does, it has a searching algorithm, so it's not just throwing darts, but it does sort of try a bunch of different combinations and just see what's cheapest to meet the hourly demand. So I hope that answers your question. There's the reason it does this huge overbuild for the 100% renewable scenario is that there's certain hours in the winter where the demand is 3.6 megawatts, and from the weather data and from the renewable resource data that Homer includes, there's not a lot of wind there, there's really no solar there, it's very cold, so batteries have trouble. So it has to build a lot of wind to meet that demand in that cold winter night. So that's why there's that big overbuild and overgeneration. But yeah.
Thank you for taking that clarification. And if you guys have ongoing discussion, the email for Dr. Lovering is on that introductory slide, and I would invite you to continue the discussion offline. Do you think the current do you think the current licensing model for the US NRC, assuming the US licenses these microreactors, will allow for rapid deportation of these reactors with site permits and whatnot? If not, do you think Part 53 development will improve this?
I say yes to both. I think right now with the current licensing structure that's in place, microreactor developers are being kind of creative and sort of pushing for flexibility in existing regulations. So it's kind of, working within the system that we have now to get these first demonstrations built. And it looks like there's, the NRC is willing to be flexible and willing to hear their arguments on these. But that's not going to work for, mass deployment. So I think also the Part 53, which is in development, a new way to license, or a new system for licensing non-light water reactors, is going to be really important as well. And it's important to make sure we get that right. So there are lots of people helping with that right now. But yeah, there's going to be people building in the current system and people licensing under Part 53.
Great, thank you. Probably somewhat related, for microreactors, what's the magnitude and impact of regulatory costs?
It can be quite large because right now, because a lot of the fee structure is based on reactor rather than megawatts. So there have been some modernization efforts in recent legislation to scale regulatory costs more towards size of reactors, and but it is a big burden for these companies, particularly the first of a kind, or that the first companies to go through licensing are paying a big sort of cost premium to get their designs through first. And that's something that future legislation can help with in helping fund NRC in a way that supports developers. So funding it more like how our federal Food and Drug Administration is funded, kind of recognizing the importance of innovation for the general public, and funding the regulatory agency for that. Right now, because the NRC is mostly fee-based, it's really a burden on the developer, but that is changing slowly with recent legislation, NEMA, and that's passed. So yeah, there could be more done, but we've seen some good progress already.
Right, thank you. Which is faster deployment, LWR type reactors, type microreactor, or non-water coolant type? And among the many SMR concepts, which SMR do you think will be the fastest commercial operation?
So I think it's going to be different for SMRs and microreactors. There's really not a microreactor that's a light water reactor. They're mostly going for non-light water reactors for the under 10 megawatt range. You do see some that are scaled down kind of SMR, but I don't think those are going to be the first to be built. I think for SMRs, you'll probably see light water reactors first, just because regulatory or regulators have a lot more experience with light water reactors. Supply chain is much better for light water reactors. So I think in a lot of countries, not just the US, but Russia and China are going to see light water reactor SMRs first. But there are unique benefits in terms of size and density and core lifetime from non-light water reactor designs that could be attractive. So yeah, I think it's going to be a non-light water reactor for microreactor and probably a light water reactor for an SMR first.
Thank you. Will microreactors likely be deployed as standalone facilities or clustered together at a facility?
Depends on the customer. I think you're going to have a diversity, and that's what's nice about them. You see this with batteries, of course, and I think you'll see the same thing with microreactors. So for these case studies that I looked at, for the community, the larger community in Canada, it deploys, 3 or 4 units. And an important thing there is that you want to have some redundancy. Having your entire community depend on one microreactor is dangerous, because what if it needs to be shut down for maintenance? And if you're off grid, that doesn't make sense. So I think you'll definitely see a mix, even if it's not multiple microreactors. You might see, reactor plus diesel, or multiple microreactors. And I think for certain industrial applications, see like one microreactor come online, and then they can add on to it as their need grows or as they get more comfortable with the technology. If you're currently operating with diesel or natural gas, you can kind of slowly replace your capacity with nuclear as your diesel generators reach the end of their life, or as you find financing. So that's a much more attractive model. I think for commercial enterprises and industrial enterprises, if they can slowly replace their generators rather than have to make this big upfront investment in the switchover.
Wow, I don't even know what else I can say besides wow, what a fantastic Q&A session, and thank you so much for such wonderful discussion. I will have to go back and look, but I think the number of questions and the level of engagement is record-breaking for your presentation, and I can't thank you enough for sharing your expertise and time with us today. And thanks to the participants who hung on through fabulous discussion. 8 o'clock my time, so that, yeah, we've definitely taken up time, and I can't thank you enough.
Yeah, thank you so much.
Is something that I think people will definitely look forward to as a newcomer into the industry, and the winner of a Pitch Your PhD competition. Holy cow! Mark down Dr. Levering's name and watch for her works coming, because I think you can tell that this will be a voice in the industry to come.
Oh, thank you so much, and thank you for all the wonderful questions. And I do encourage people to email me if they have more, or if they want to talk further.
Great. Thank you, everyone. Bye-bye.